Given that y is equal to arcsine x, we want to show that dy dx is 1 over the square root of 1 minus x squared. So let's start with y is arcsine x. Take the sine of both sides and we get sine y is equal to x. Differentiate both sides with respect to x. That means we're doing implicit differentiation on this left-hand side. Sine differentiates to cos, so we get cos y. But we also need to multiply by dy dx because we were differentiating with respect to x. Differentiating x with respect to x gives us 1. So dy dx is equal to 1 over cos y. Now remember that sine squared theta plus cos squared theta is equal to 1. So cos squared theta is equal to 1 minus sine squared theta. And cos theta will then be the square root of 1 minus sine squared theta. So this is equal to 1 over the square root of 1 minus sine squared y. But from this line we know that sine y is equal to x, and therefore that's dy dx is 1 over the square root of 1 minus x squared as required. Now in part B we've got f of x is arcsine e to the x. Prove that f of x has no stationary points. So we want to look at the first differential. We have this, and we know the chain rule. So we're going to have 1 over the square root of 1 take away e to the 2x, which is e to the x squared. And then you have to multiply by the differential of the inside function. So that's e to the x. So what we have is e to the x over the square root of 1 take away e to the 2x. For f dashed x to be equal to 0, that would mean e to the x is equal to 0, which has no solutions.